action. All right, come back and action. Love it. Okay. So, BJC Lecture 4, Take 1, Creativity. All right. Okay, here we go. Okay, here we go. Ready? 3, 2... Wait, I got 3? What's 3 mean? 3 means good. That's okay? This is like 3. Yeah. Does this mean keep going? So this means like slow down, and this means keep going, right? Okay. That's our funny hands. Okay, here we go. I'm having fun. All right. 3, 2, and... All right, welcome back, folks. We're doing a new topic. This is creativity, and this is one of the big ideas we're going to see in the APCS Principles curriculum. So there were 7 big ideas, and one of the really important ones, listed first, actually, is creativity. So let's talk a little bit about what that means. So the first thing is, over the course of the next couple of lectures on creativity that you're going to see, many things you may notice seem common sense to you. And it's okay, but we really want to make sure that there isn't somebody out there who doesn't know all of these things. So we're going to say some things that we probably most of you know, but if there's somebody out there that's learning something new, then we've done our job, okay? So bear with us if you've seen this before. So this is a quote, and I usually don't like to read quotes, so maybe I'll let you read this on the side, that talks about how computing is a creative activity. And people may not realize that. So you're reading as I'm talking. People may think, okay, if you're doing computer science or computing, that's probably not creative. Creative are artists, right? The people who wear cool-looking clothes and cool-looking hats. By the way, I'm deciding to be creative with my attire today, just trying to give you a little taste of what creative in the sartorial sense is, right? I'll let you look that up. So then, you've got people who think, okay, the artists, they're the creative ones, but people with the computers, they're not. I'll give you an example. Pixar is a wonderful place to work. And when you walk in their front door, if you turn to the left, turn to the right, it's the artist's area. If you turn to the left, you're right. It's the technical area, the technical, kind of the people who write the code, people who do the programming, people who write the tools. And you're thinking, well, okay, that means creative people go that way, and non-creative people go that way. And that's totally wrong. There are creative people going both ways. There's so much creativity in making the software, and making the tools, and working with the users, and doing the really hard engineering. There's so much creativity in that side, too. So there's the misperception. It's only the people who are the artists who are creative. Totally wrong. Software engineers are artists. It's wonderful. So the idea is that we also, part of this, the blurb talks about solving problems. Some of the things we're going to build, some of these computational artifacts, things you build with computers, can solve real problems and help people, and also explore personal interests. That's one of the things we're talking about. So this course is going to support, this course in general, and the CS Principles in general, support creativity, creative uses of computing, and supporting and flowing and letting that grow. In fact, the 2 big assignments you're going to do are an Explorer, where you're going to do some research about innovation, and the techniques that went into building the innovation were creative, and writing your own programs, both as a partnership and individually, and we hope there's tons of creativity in both of the performance tasks you're going to see. Okay? So, creative development can be an essential process for creating computational artifacts. So, as you're building an artifact, something created with a computer, there's a creative process involved. So there's not just creativity. Creativity kind of describes a process, right? And so the process is the following. I'll just kind of the highlight words, which say part of what makes a process creative is that A, it uses a non-traditional form. It's something that hasn't been done before, okay? Also, it could use novel techniques. So maybe I have this great example. Maybe rather than kind of drawing something, and it's, that's the traditional ways you might draw a picture, right? Or make an abstract picture. Wouldn't it be amazing to use computation in a creative way? Watch this. You have a video camera. It faces a fishbowl with a single fish inside. You have software that you've written to track the fish. That fish, now, that XY position of the fish, now drives a virtual paintbrush. And so now the fish is painting the picture. You get it? If it swim back and forth, then the paintbrush goes back and forth. That would be an incredible novel technique to tie together the idea of filming, of image recognition, that the fish is actually painting the picture. Wouldn't that be a cool thing, right? Imagine combining things in amazing ways. So many things are connected to the internet now, Internet of Things, that you can imagine having, when I walk out of the house, my Fitbit knows that I'm leaving the house, and so automatically it signals my Nest to turn the power down, to turn off my lights, or checking to see whether it's nighttime. If it's nighttime, I'm turning on my Christmas lights. Like all these things where you could plug in sensors and output devices, and a robot waves his hand goodbye to me as I'm leaving because it knows I'm like an amazing creative ways to tie things together in a really powerful idea. So that's like tying things together and remixing things as well. That's all these things are creative, and it's part about the process. So non-traditional techniques and novel combinations that maybe not have been seen before. So it's kind of new things. Creative means like a process. It's also about things you've never seen before. Okay? So part of the process can also be iterative, which means you might try to create the software with the fish driving it, and you try one thing, it doesn't work so much, because maybe you look from the top down. Maybe the fish only goes like this from the top down, but from the side it goes up and down. So maybe you tried the first time, it didn't work so well. You get all these pictures of painting 1, left and right, painting 2, left and right, because you're looking from the top down on the fish, because maybe that's an easy way to put your tripod. But next time you say, what if I had it from the side? Okay, well the next iteration, the next time you try it again. So it's an iterative technique where you try something, if you don't like it, you try it again, and you try it again until you're happy. So the iterative process is part of the creative process. It's not just, you don't just think that all the artists draw the picture first and it's done. No, they draw sketches, they don't like it, draw sketches, they throw it away. The same thing with computation. You'll try something, you don't like it, you make an adjustment, and thankfully, you don't usually throw things away. If you make a sculpture, you don't like it, you throw it away, start again. But with your computational artifact, you can have code that does something, and you just adjust the camera or adjust the software. You don't have to start from over. But sometimes you just start over, and that's okay too. So there's an exploratory process involved as well. You might not know where you're going to go, and just the fact that you're walking through the woods and exploring the space. What if I try this? Well, that didn't work. I tried putting the camera on my dog. That didn't work. Oh, the fish worked. So you're exploring the space of this creative thing. So it's exploratory, it's iterative in that process, as well as having novel combinations and as well as having non-traditional techniques. Okay, so that's the summary of kind of what creativity is, and we'll talk about creativity more in the next video. Pink. All right, so questions before we do the clicker question. Did you guys get that? A couple of the key issues, right? So it's non-prescribed, meaning no one's telling you how to do that, okay? That's to be creative, right? It's an iterative, where you're trying it over and over until you're happy. The artistic part of you or the scientific part of you is happy with something. Maybe you're doing something that's not artistic. Maybe you're doing something scientific. You're trying to get a simulation of traffic, and the first model doesn't work, and the second model doesn't work, and you keep doing that in a space that's iterative as you keep doing it. You're creative in how you're exploring the hard problem, but it's still an iterative technique, even if the output is not necessarily something that's artistic. It might be an actual simulation with real hard science in there, okay? Questions at all about that before we do a clicker? Okay. This should be probably a pretty easy clicker. Let's try it. Here we go. Let me boot my clicker software real fast. And here we go. Okay, clicker. Get this. CS1, choose. Start session. And while this is doing this over here, can I move this window? I can. All right. Here is the clicker question. Go. Which of these is not? It's really hard to call something not creative because so many things are. But of these 4, which of these is not creative? Okay? For your final project, A, you do it any way you want and end up using a novel technique. B, you do it any way you want, but you end up using a tried and true style or technique. C, your teacher tells you how to do it, but it's a technique never done before. Or D, teacher tells you how to do it, and it's a tried and true technique. So of those 4, it's hard to say something's not ever, but which is the least? I should say which is the least. Okay? Which is the least creative, A through, and it should be going, right? Okay, let's see if we can get more than 150 this time. I think we got 120-ish last time. Okay? All right. Maybe this is an easy one. Let me see how the numbers are coming up. Uh-oh. Too easy. I'm not going to let you talk to your neighbors. Way too easy. Okay. 3, 2, 1, stop. And, all right, that wasn't a good question. Because that was too easy. But the key was, you could have either one. To be creative, you could either go on your own way, but use an old technique, but you're still using an old technique in your own creative new way. That's valid. Like a paintbrush, right? Paintbrush, a million people have done paintbrushes, but I'm painting in my way. Okay? Or you could, so that's, the way is the clever thing, or you could have a choice of the kind of style, kind of how to do it, okay? So kind of how to use the paintbrush is your way. So it's kind of like both how to do it and the technique are two independent things. So we're saying if you're lacking both of them, If your teacher's telling you what to do, they're prescribing, right? Non-prescribed is creative. They're prescribing how to do it, and they say the way to do it is the way that everyone's always ever done it. But what's the cool thing is C is not. Teacher says, look, I'm going to tell you how to do it. I'm going to tell you, I'm going to prescribe to you how to do it, but I'm going to make up a new crazy way that's never been done before. Then that's still creative, right? Because you're doing it, even though they told you, it's still no one's ever done it before. Even though they told you, it's still creative because it's very new, right? So if it's all tried and true and you have no choice at all, if it's just boring, the same way it's always ever been done, and you have no choice, no way for your personal creativity to just shine through it all, then that's not creative, obviously. That was too easy. Let's keep moving on. Okay, it's hard to write hard questions for this, by the way. This is a parenthetical. Okay, let's come on back. Take a little sippy sip. All right, here we go. Okay, and how we doing? Do a quickie check. Thumbs up. All right, 3, 2. All right, welcome back. We're still talking about creativity, and now we're going to talk about computational artifacts. So, first we'll mention what computing enables people to do. And this is a beautiful rendering of a poster for a graphical series. So computing enables people, I'll read this from it, to use creative development processes, which we just talked about the processes before, to create artifacts. And I almost want to have now a shorthand, because I'm going to say the phrase computational artifacts about 25 times in the next video. So I'm going to say CA. It's my new shorthand. No one else uses this, but it's for me. To CA. To create CA, computational artifacts, for creative expression or to solve a problem. And it's really important that I mention this. Those two are both valid. It means, as you're making a CA, a computational artifact, I'll show what that is in the next thing. As you're making something with a computer, that's what it is. That CA can either be for creative expression. People always think, oh, it's always for creative expression. You know, whenever you make a computational artifact, it's because you care about it. Like people write a novel. They write a novel using a word processor. That is using a computer to make your own creative expression of your own story. But it could also be solving a problem. Someone says, boy, we got to design a bridge. That bridge is a problem. I need a bridge to span these two coasts. What do? You can be using creativity in that total solve a problem model, right? The problem was given to you as needed to do, and you're using creativity in your engineering, in your software development, in all the processes you do, okay? So there's lots of ways that creativity can come into, and when you're making a CA, that CA could either be used to solve a problem or for purely creative expression, and that's wonderful too, and celebrated too, and valid. It's really important. It's valid also, okay? So when you're choosing projects, the community online and the community here locally, when you're choosing your projects for the create task, you can either choose it kind of on is it a solve a problem type, and that's valid, 100% valid, or do you just want to make something that you always wanted to make just for yourself, and that's also valid too, okay? That's the first one. So a computational artifact, a CA, is something that a human uses a computer to build. That's it. And one of the great examples we talk about is maybe software. You can use, in the classes, obviously, programming is emphasized, so maybe software is an artifact. It turns out, here's this cool thing, watch. Let's say you make a drawing program, kind of an auto drawer that'll make a random thing and draw around in random things, okay? Here's what's cool about this. The program you wrote, that's a CA. That's a computational artifact. Watch this. The picture that your program drew is also a computational artifact. Even though you didn't do it, you kind of had your hand in what made it. But the picture itself is also a CA. Isn't that kind of neat? So it's not just the program, but the output of the program. Isn't that kind of neat that here's the program and its output, and both of those were CAs. Both of those are computational artifacts, okay? And obviously, if it's something that uses a computer, then you have to use software tools and services to do that. That's the piece of that. So these computational tools and techniques. So the tools and techniques for this, okay, are used to make the artifacts. We've seen that before, okay? And they include, but not limited to, now let's think of the things that you use a computer to do, to make CAs. Well, how about a programming interface? So here's a picture of Snap, right there, a beautiful picture of Snap. And Snap's a beautiful, hopefully graphical and hopefully fun and friendly interface for using a computer to make a CA, in this case making programs, okay? That's easy. You can also, so it also says, a creatively developed CA has non-traditional techniques. We said that already before. That's a repeat here, okay? It reflects personal interests, so you're bringing your interests into the process. All that said before, okay? And here's the interesting thing. These techniques can enhance the process of finding a solution. So remember, you want to sometimes solve a problem. computation can help you get to that solution. So, I need to figure out exactly what the load is I can put on this bridge. Well, you can use non-computer techniques or computing techniques to find out what the maximum load that a bridge could handle. And obviously, you should probably know this. Again, a lot of this is very common sense. Computing can help with the process of finding the solution. So computing can help with your creativity, if you choose a creative problem, or it can help with the actual solve a problem part, because computing can be used to verify and test and run 1,000 numbers through it and do simulations and all those wonderful things, okay? Last slide before we cut. A creatively developed process, okay? A creative development process for creating CAs can be used, as I said, to solve problems here's when traditional techniques don't work. So a traditional technique might mean we tried something the same way, and we're not getting any closer to the solution. Well, let's have a creative kind of response to that to think about how to get out of the box. Out of the box thinking is kind of what that's saying to get to that solution. Okay? And here's an interesting idea. You can create artifacts new. People often think, well, you have to start new. I'm starting from ground, and here's my novel. No. You can create these artifacts by remixing. The idea of remixing is now very popular, but it wasn't 10 years ago. People thought you have to start from the beginning. You didn't think you could kind of take code from here, take code from here, and put code together and make that as like this remix of code from here that does some powerful stuff. Or take a picture from here, picture from here, picture from here, and using digital techniques, people have done collages and cut things out of newspapers for years. But only recently has maybe 20 years, has photo editing software made it easy enough that I can just grab pictures around, and the web is now online. I can grab pictures and cut them together and paste them together to make a whole new thing that reflects my creative style. And here's a beautiful picture of a remix, okay, of digitally manipulated photos of the artist and the Mona Lisa together as like overlaid. Like, oh, isn't that cool? That kind of his face is kind of seen in her face if you compare them. Beautiful. And it sends a message of like, wow, see, when you're a painter, you're actually reflecting your own sensibilities and maybe your own personality or maybe your own face into your art. It's just beautiful to kind of connect with that. So another piece of it is computation helps you with enhanced precision and detail. My great example, I had some folks work on our BJCX team help me with some of these examples, which is think about the photo editing process. And in the early days before computation, you were in a dark room, and you were trying to dodge and burn and try to lighten or darken an area of your print you're trying to make. In your dark room, it's all lights, and you're doing this. In Photoshop and in other photo editing software, you get incredible more detail. I can zoom all the way in and do things at a level of detail and precision I never could have in a dark room process. Okay, so it's a really great example of how computational is helping you in the process of making your creative artifact. With more detail and precision. And finally, as I talked about before, the key thing in all this is creativity at the core of it. At the core of the whole thing is about your personal interest. It's your personal interest that has to be reflected in the artifact you're making. Okay? We'll learn more about artifacts and their power and limitations and even how you make them in the next video. Cut. All right. So, questions about this before we go to the clicker question? So this is, again, a lot of things you've heard before. Just need to kind of get them out there for those who, I didn't realize that you can actually be creative and you're solving a problem for somebody else. That's kind of maybe new for you, right? So a couple of things you might have heard that are a little bit new, maybe not so much. This is not so. This, by the way, just as a general thing, I'll try to tell you how much your brain should hurt every lecture. This is not one of those brain hurt lectures. The last one with the binary, that was harder. And it's going to get harder. Also, I'll tell you when it's going to be ready for the stretch your brain and kind of crack your brain knuckles to get ready. All right, here we go. Ready for clickers? Here we go. And... oh, I left my clicker picture up. I shouldn't have done that. That wasn't so good. Yeah. All right. Maybe if I move it to the corner, the top corner like that, like way up, then it's easy to cut it back and fix it. Okay. All right. Which benefits from computation? And remember, it's hard to write a hard question here. So any questions about creativity is probably going to be pretty easy. I found it's really hard to write a hard question when I was trying to write some questions here. So, and maybe this is also trivial. Man, oh man. All right, let's get in here quickly. Which benefits either precision or detail or in terms of speed or anything. So let's go to this and let's see what we got here. This is possibly the easiest question ever. So you're going to thank me on the exam also for asking a creativity question. Look, that was a nice one. Easy kind of thing. All right, here we go. 3, 2, 1, let's stop. And yes, way too easy. And all of the above. All of these things benefit. And many of them, if I were going to ask a harder question, I'd say how. How is each of these guys benefiting from that? And you might say, oh, I can undo, right? That's an obvious thing. Or I can try something with higher precision here. Or in terms of the overall time it takes me to do something. By the way, it's not always the case that computation makes things easier, right? If I have to what's a simple thing, a very simple manual thing, hammer a nail into a piece of wood. I don't know of a way that computation can help me with that kind of a thing. I mean, maybe I could build a robot that has power and knows how to grip, and 10 years later I have a robot that knows how to grip a piece of thing and knows how hard to hit it. And no, I can just do it faster there. So it's not like computation always is the panacea, but many, many, many things computation will help you with in your life, okay? So not the case always, but many, many, many things. All right. I'm going to leave this guy up here, and then I think I can cut it off. I can cut him off in the top, because the top never actually changes. So that's a good way to play that. Okay. So, any questions about this so far? Pretty easy, I hope. Not too bad. And we're learning a lot about creativity. And now, this is the last one. This is the last of the three. And if I have enough time, which I think I will, which is great, I'm going to show you some of the greatest projects ever. I'll demo those for you. So it's kind of get rid of this creative description stuff to get to see the demos, hopefully. And then, here's the other cool thing. I'm going to show you this great video about grit. We'll talk about that, okay? So, get my water here. I'll mark a ruby on the side. Mm-hmm. All right, here we go. Okay. 3, 2. All right, folks, welcome back. Now we're talking about the last aspect of creativity we're going to talk about today, which is collaboration, analysis, and the power of creative artifacts, computational artifacts. Okay? So, now we're talking about the process of making something creatively. And many people think that, look, all the brilliant geniuses that have made things make them alone in a basement or in a garage. We're near Silicon Valley, in a garage. Not the case at all. So many people, during the process, have collaboration, where they're working together to make that artifact. They're working together to make that new innovation. It's very rare, really is very rare, that from start to finish, someone did it all on their own. It's just so hard these days with all of the possibilities that other aspects, other diverse opinions might benefit, that someone would think that only one opinion and that thing taken from start to finish is better to have one person's opinion. Now, sometimes there's a leader who has their drive. The founder might have their vision for how it works, but they still have collaborators all throughout that help influence and shape and polish. You can think of collaborators in some sense as people who all have a little bit of very fine, abrasive sandpaper. And each one of them is kind of helping polish your sculpture in different angles. I'm really good at knees, so I'm going to go over and polish. Oh, now the knees are perfect, now thanks to my. So each person has their little angle on what they can polish. Maybe I'm really good at, this might work for one group of students, but not other groups. So I might be really good about thinking about a lot diverse group of students that a particular software might work for. So it's really great to have collaborative influences to the process. So collaboration is, first, just definition, very simple, work in the building of something that's more than one person, okay, not just one individual. Here's the interesting thing. Effective collaboration, now that we have the internet, we're going to learn a lot about the internet later in this semester, the power is in these online collaborative tools. There's a ton of tools out there that are free, often free, that'll let you work collaboratively when you're not in the same place. So now we've bought into the idea that collaboration can help. We'll talk a little bit more later. But how do you make it happen if you're not in the same place? And there's amazing tools that'll, right now, free, allow people to both have conferencing. So, here's here's a picture of my sketch, and then you're looking and saying, well, I might add a little thing here, the bridge, and stretch it here, maybe have a bike lane. Okay, so we're talking online. You can also have documents that you're working on together. Most of you have done this before. If you haven't, I encourage you to try this. Google Docs is a great start because it's all free. So you and a partner, or maybe multiple partners, are working on together a presentation, or you're writing an essay, or you're writing a grant proposal. This is very common, where many of us are trying to get money from agencies to teach stuff and to do interesting, innovative things in computer science education, and we're collaboratively working on these grants together. And there's 10 people all in the same document, all polishing in their way, which is really fun to watch who's good at the which versus that. Who's good at capitalization? Who's good at the flow? Who's good at, I don't get from 10 miles up, I'm not getting the message, Who's good at different people? Each of us is adding our different aspect in that collaboration. It's wonderful. It can also be hard. It's not always easy, right? It could be that I have a vision for taking the essay or the picture or the sculpture this way, and one of my collaborators wants to take it this way, and there's a tug of war. And that's always a tension, and that's always hard. So it's not always easy, but sometimes you end up I think it should be A, You think it should be B. It turns out, after thinking about it, turns out that C makes us all happy and is better than A or B. Sometimes you go to a better place where it's a win-win, where it's actually better thanks to each of you, and it doesn't have to be only A or B, which is an important thing. So, in terms of the process, I just kind of was waxing about the tension. One of the bullet 3 says, effective collaboration, practice a couple of things. Interpersonal communication, consensus building. So it's trying to get everybody on the same team with that. Conflict resolution. How do you work successfully, collaboratively? Well, when you have conflict, you have to figure out how to resolve the conflict and how to have all the voices heard and how to have not just the loudest person win, right? If you had no training in how to work in a team successfully, you may have, by default, the loudest, strongest, biggest person wins. Or the person with the most money, or the most influence. All those are the wrong thing. The right thing for successful collaboration is when all the voices are heard and you come up to consensus where everyone feels like that's the right decision together. And as I said, sometimes it isn't A or B, sometimes actually it's a C that you didn't think about. And so kind of exploring all the spaces is important as well. Okay? Negotiation. All right, maybe I'll give a little bit on this one, but you give me on this one, so we're both kind of happy at the end and so everybody feels like they've not just lost every decision. Okay, that's important too. So effective collaboration strategies enhances performance. The team is better. If the team does these successful collaboration, the team will be more successful. The output will be better. Okay. Multiple perspectives. So another piece of it is, one of the reasons that the diverse perspectives are so wonderful is a single group. There might be 5 people, but if you don't have a diverse kind of group of folks influencing the design, you may only have things that are appealing to a certain group. You might have a certain group where they're from, what they're like, demographics, all those things factor in, but you need to have diversity on many opinions. Otherwise, you kind of don't have, we didn't think about, because nobody on our team has that, right? I didn't think about, I'm quite tall myself, so let's say I had a team of all people who were really, really tall. We don't think about what happens if you're much taller than me or much shorter than me, because we're all the same height, or something like that. So you want to have a diverse opinion of many different angles, okay? And finally, you want to be able to, again, have that personal connection to the creativity reflected in the collaborative design. It's an important thing. Now, once you've built your collaborative artifact, your computational artifact collaboratively or non-collaboratively, you can do analysis of it. So you built something. Here it is. It's in my hand. Well, you can look at it from different lenses. Okay? How effective is it at solving a problem? The problem it was asked to solve. How effective is it at sharing the vision? Let's say it's a story. Let's say this is a story for the next Pixar film. And they collaboratively work together using computational tools like, online authoring, Google Docsy things to make something. Well, you can now have an angle. How does that story sound? How does it make you feel? Okay? So the computational artifact, the thing created with a computer, can have an analysis that has many different lenses to it. So you can look at it with correctness. Does it solve the problem? Is it useful? Usability? Okay? What's its functionality? This piece of software is really hard to use. You have to put all these arguments in. The lines, it's too hard to find. The usability can be a lot of different angles to it. Okay? And suitability. Does it actually work in terms of being suited for what the task you're going to be using it for? This is kind of a general thing because it depends on the particular artifact you're thinking about. It might have weaknesses. Right? I might have to, here's a picture. I had these screws to put in. And I make this computational artifact, and I build this amazing hammer. It's not the right tool, right? So it might not have it might have weaknesses. Well, it's nice if I really want to squash the wood, but it doesn't really kind of grip, and it threads the wood with a screw. It's harder than a nail, so that didn't work. So it might have some weaknesses, have some mistakes and errors. Those mistakes and errors may not be seen. How about this one? It may have mistakes that are actually not visible. So I might have something that renders a picture. And in the bottom right corner, it actually draws a really evil-looking face, but it's really subtle. It's really subtle. So nobody can see it, but it's still bad. My software had a bug, and it draws a really mean, angry face. But most people can't see it. Even though it has kind of an error, that face wasn't supposed to be there. I could make an audio software that actually randomly generates music. And I program it, make it riff like Jimi Hendrix guitar riff. And if you zoom in, it actually goes really high frequency. But no one can hear that because our audio operates in this 20 hertz, 20 kilohertz thing. But in fact, it shouldn't be wiggling. It should be flat during the quiet period. But it's not. It's not flat. It has noise. But no one's hearing it because our ears don't work like that. It's still an error, but you can't see it based on your perception. Okay? And finally, here's the piece of part of it. The functionality, I talked about how functional is this, or appropriateness, okay? depends on how it's used or perceived. So in some sense, what that means is, I think, this is a harder one to get to right here. But in some sense it says, I'm thinking this is going to be used for that technique. Turns out it's really supposed to be meant for that one. So I'm deciding it's not appropriate because I think it's being used for the wrong thing. It's supposed to be used for that. So I think, okay, I don't know what the tool is, but you make this great thing. It looks like it's really a hammer, but it looks like this weird thing with a metal part and a stick. Boy, that must be used for screws because they kind of have a round head and they're supposed to go into wood. So I'm going to say that's inappropriate for driving things into wood because I'm having the wrong context for it. It's great as a tool. Every carpenter has a hammer, but because the perception of kind of the context of what I was going to use that artifact for was the wrong one, I'm evaluating it as a very poor functionality. In fact, it has great functionality for what it's meant to do, but I'm thinking about it in the wrong context. Okay, so that's what the bottom one says. Okay, last slide. Computation transforms industries. Just transforms industries. Okay? And you probably know that. It's called disruptive technology. Okay? So here's an example. Here's just some examples. Not all, but here's some examples of the industries that have been transformed. Digital, audio, and music industries. Can you imagine trying to be an editor of, the next big Beyonce hit? If you didn't have a computer to go back and do this, you had to actually have it on tape and listen to it and go back on tape and be cutting and mixing with analog tape. Hard. And you're having loss in the process because it's all analog and the next generation it has more noise than the earlier generation. No. Nobody right now in the digital audio editing process doesn't use a computer. Everyone uses a computer. They all have a big screen and the waveforms and they're cutting and blending and mixing and hearing it. Oh, that's too low. Raise it up. And it's just so beautiful to watch the process of the editors use the computers for these things. Transform the industries in ways that and transform the industry not just in how to mix it, but how to ship it. Right? Now you give them MP3 file, the WAV file, back to the artist. The artist can now decide, put it on the internet for free. It now goes viral. And in one day, there's songs on every person's ears in the world. Are you kidding me? How the fact that this is digital, this is also part of Blown to Bits. By the way, we encourage you to read Blown to Bits. That part of that is saying when things go to become bits, things just change. That artist can share that song and the next day the whole world can hear it. Are you kidding me? Could never have happened with physical media, with non-computers and non-transformative. So it's totally transformed the audio industry. How about digital images? How about the idea that you can't trust images anymore? I can take a picture, I can Photoshop in different things, I can put a Bigfoot, someone says, I found Bigfoot. Oh yeah, right, Photoshop. I mean, you have all these things. Oh, here's a beautiful, beautiful model. Oh yeah, Photoshop, right? The idea that you can't trust pictures anymore has transformed all of photography, all of print media. The idea that you can just keep editing and editing and editing rather than having to go back to the darkroom and do that it's just, no one wants to do that anymore. Digital effects and animation. I did my PhD in computer graphics. So the idea that you would have an animation hand-drawn, and that's nice, except that if I want to do fully capture a 3D scene with lighting that feels realistic, to have to draw that, the artistic ability to have to draw the next Snow White is just unbelievable. To get the lighting right. Snow White's rendered very flat, actually. Pretty flat. Because it's really hard to do the subtle shading on how the shadows fall on Snow White's dress. But the computer just says, oh, here's a shape, here's a lighting simulation, boom, all of a sudden you have all the beautiful subtle textures of a pattern print as she dances and swirls in a dance. Are you kidding me? How hard that would be without a computer? Transform the computer like you can't even imagine. And the idea that you can have asset management as you're making 3D models and as you're rendering them and changing the lights, all that is all done with computers. Effects, every single movie you see in the summers now have digital effects to remove the wires from the stunt people or to add a monster like in BattleBotsy kind of a thing. You end up having almost all the blockbusters in the summer have tremendous digital enhancements to them. So it's completely changed the effects industry. And here's just a beautiful picture of a 3D jack, just in terms of the 3D, in terms of the do-it-yourself space. Think about the do-it-yourself space, that now people can design something and like a jack and then print it. And in fact, as a surprise, watch this. I have for you some things that I have printed on my personal printer. Hope I can get this in picture. This is a Taurus knot. This is in terms of creativity and transform industries. The do-it-yourself industry. On my own printer is a Taurus knot. Look at this. This is a beautiful set of pyramids that are intertwined and locked together. I could pass these around as well. I'm just hoping to get this on camera. This is a shape called the Menger cube. And if you turn it around, if you slice it, it ends up having a beautiful pattern in the back that I had never even imagined. Unless I had sliced it and printed it myself, I wouldn't have seen. And this is now 3 intersecting dodecahedron. Just beautiful. So in terms of transforming the do-it-yourself space and the creative artistic math and art space, I would never be able to sculpt this. But I now can, in my home, design this and print it, and it's amazing. So it's transformed that industry as well. And finally, before we end up at the last thing to say about computation and creativity and computational artifacts is that you can explore real and virtual phenomena. So you can use computation to explore real phenomena like weather and run a simulation, like traffic and run a simulation, other things. You can use it to drink in data and get down there. But you can also explore virtual phenomena, which kind of connects with my 3D sense. Which you can create a 3D world that's never been thought of before. And you're using the computation and software to build the 3D world, to render the 3D world. And now I'm hearing that the new Oculus Rift VR allows you to explore it in a virtual space. I can't wait. They've talked about having virtual movies now. VR movies where you're putting on the lens and you're watching a movie, but you're in the space. And so there was a demo that somebody showed where a bull came at them, and everyone who had the lenses on felt the bull was coming at them. Some person actually fell back like, ah! I mean, the level of engagement when you're there rather than passively thinking, oh, it's happening to the actors. No, it's happening to me. Imagine that space. So and all those are virtual phenomena they're creating. So the idea is computation can be used for all of these wonderful things. Creativity is about your own personal expression. Collaboration is part of the successful way that teams work together using tools to make these artifacts together. And once you've made the artifacts, you can analyze them in many ways. And in summary, we've transformed industries. Computation is just amazing, folks. All right, that's the last lecture on creativity. We'll see you next time. All right, great. Questions about that last little bit? Now, I think we have a lot of time, hopefully left. Let me see. I got 10 minutes, okay? 10 minutes. Any questions on that last little bit? I got through creativity with enough time. I can show you some of the best projects in history in CS10. You guys want to see them? Yeah, let's rock and roll? Awesome. All right. So, oh, by the way, I'll pass these around. Let me pass these around here. You can do this here quick. I grab some there. You can check it out here. And over here, there's that one. And pass these around. Okay, and I'll just click them back at the end. Okay, here we go. So, first, here we go. Ready? And action. Okay, the first demo I'm going to show you is from a demo called Magic Machine. Magic Machine, I'm going to show you, I'm not saying the best for last, this is the best first. Magic Machine is the most incredible student project in history in CS10 I've ever seen, in BJC. Okay? Here's how it works. Okay? Let me first get out of the iClicker and get here. Okay? I'm still recording. So watch it. Here we go. Ready? So I go to this. Okay? And I say go. Maybe some of you have heard of loops before. Watch this. I put a thing here, right there. Put a dot there, and watch what happens. Whoa. Interesting. I have no idea about music, but I'm being creative. This, by the way, is called generative software. That's not going to be on exam. Generative software is open-ended software that lets you do something above and beyond what the original author intended. So like a word processor. The person building a word processor never knows what novel you're going to write, right? So it allows you to have an open, explorative space for that. So I'm using this software to make a song that they never have thought of me making before. So I'm using this as a kind of a tool to do this in an incredible way. Is this unbelievable? This is just so cool. And what's also cool is I can change the instruments. And watch, if I click again, it goes, I think I can say erase, and I can go off, watch. So I can now clean this up a little bit. And like, it gets quieter. It's like now the band's going home. Band's going home. Huh? Okay. BYOB is the earlier version of Snap, and this is called Magic Machine. Easily, I think, the greatest project I've ever seen. Let me just give some background. I think 2 or 3 students did this project. They had never programmed before. Like many of you, never programmed before. They went to this class, and by the 12th week, because this is a 3-week project, by the 12th week, they engaged together in an incredible collaboration, using all the techniques we talked about of successful collaboration. They worked together, pair programming all together. They worked hard. I'm not going to say, but they didn't work 70, 80, 90 hours on this. They worked a normal time that most of you worked on your project, and they were able to really fine-tune and touch base on their creative aspects. They love music. And they said, I want to make something that will let you use the graphical nature of BYOB, and it was pre-Snap of BYOB. The graphical nature lets you click and interact with it visually very easily. Those cause events. Those events add these channels. Each channel is going to be tuned the right way, and you can even, what's actually really cool, watch this, you can even do this. You can have a song that does this, has like a nice thing, okay? Now watch. I then hit mutate, and watch what happens. It thinks about it, and then kind of shakes it around a little bit. See if it takes how fast it can go. Maybe it didn't work. Let's see. It didn't work. Okay. Some things have bugs. Okay. No, the mutate was supposed to do, it was supposed to, whoa, that was cool. It's supposed to like shake it around and kind of like drop some things. Like it might move something over. It's almost like you kind of blur your eyes and like the places where the musical notes were kind of either move or added or destroy. But it's a variant, basically. It's kind of like a jazz variant like that. So I just love that feature. Anyway, so that was that one. 4 minutes left. I'm going to show you this one here quick. We're going to save the grit lecture because it's a 6-minute thing. We only have 4 minutes left. I'm going to show you this one. I showed sketch people came in early. I'm going to show you this one. This is IMBY.
Hi, I'm Colin.
I'm Haley, and this is our CS10 final project. And this is our group member, Max. He couldn't make it today for the filming of the demo.
Hope you enjoy it.
Okay, this is IMBY, which is Intelligent Maze Maneuver Bot-Yo. How IMBY works is that IMBY navigates a maze depending on obstacle detection and various rules regarding that. So our code is right here. And how it works is that when there aren't any obstacles, it's just always moving forward. And he's always checking in case there are obstacles. So once there's an obstacle, that broadcasts and goes over to this chunk of code. And one thing we should say is that with the Finch commands, there's no kind of built-in radial turns. So we had to make custom blocks that turn left or right at a certain speed for a certain amount of time, depending on how much of a turn we want him to go while he solves the maze. So here's this code, and this basically runs and figures out until there's no obstacles in front. We have a feature where if IMBY gets into a dead end, after trying to turn so many times, it'll back up, check which direction it should go that isn't the direction it just went.
Back ends are hard. In mazes, dead ends are hard to get out of. And look, but they figured out how to get it working around these dead ends. So they have a special code to do that.
The Finch is a very light robot, gets stuck really easily. We added human interaction where if you push left, he'll turn left a little, right will turn right, and that's when we get stuck on this. So here we go. We're going to do this. I'll also add that because the Finch is so light, the cord is heavier than the Finch. I'm going to hold it up.
And what's on its head?
Oh yeah, this is my iPhone. We decided it'd be really cool if we could see what IMBY sees. So we got some FaceTime run-in on the phone right there.
And it's coming right over here, so this is what IMBY's seeing. All right.
Okay, ready?
Yeah.
We have free IMBYs for you to check out for your final project if you want to do this.
Good.
All that stuff is free. We're going to give you as many pieces of software and hardware as you need to make your project successful.
He's detecting there's a wall, so he's turning.
And it even changes the color of its nose to tell whether it's like green, meaning it's good, or like red, meaning I see an obstacle.
Trying to figure out which way he can
And as you're watching this, I should say, these students never programmed before this class either.
Oh, he's backing up. So
Okay?
try again.
And they were able to make this maze, and they created this. Look, they're making cardboard
All by
mazes.
himself.
And a lot of iterative process. Clearly, MB used to get stuck in the corner. And then they added, in the iterative process, let's add things to fix that part, to adjust it to kind of get a better maze solver robot, path finder, algorithm. And you're like, no way, it's going to the corner, no. But notice, by the way, they didn't just do an easy maze that had no corners. They did a couple dead ends, and they had to show that it could actually survive the dead end. Watch it. Now, it's hard because this particular robot doesn't spin, and the back end hits the edges, so it's hard. Look at it, backed up.
Check that way.
It caught their code that handles the dead ends, and it worked. Look at that.
Good job.
I know this is another big dead end. Let's see if we can get this one. This is hard. I should play this on. Can you play this on double speed, Michael? How do you do that? Right there?
Second dead end, indeed.
Oh, there we go. Thank you.
What's MB seeing?
Perfect. I should play the whole thing on double speed, actually.
Here we go. Back on this, buddy. Oh man, he got stuck. He's gonna go back out that end. He got confused.
Come on, MB. Come on. And you'll get a chance to make a video of your final project too. So you get a chance to. Come on, MB. Come on, MB. Stay for the end because it's gonna be funny with the cat. Watch. Yes. Watch the cat. Watch the cat. All right, folks. Thanks so much. That's a creativity lecture. Yay! Good job.